Are you able to see my PPT?
Sir.
Okay, this is what we're at. So we are done a momentum balance, shell balance for momentum transfer. For our problem, we had only Z momentum because we have only Z velocity. So after rearranging everything and substituting all the information, this is what we will get a differential equation. First, a differential equation, which is the differential equation of a, momentum flux actually. Tau xz, d by dx of tau xz equals to rho g cos of beta. Now this is first order differential equation. To get the profile equation for this momentum transfer, what I need is a one boundary condition, at least one boundary condition is needed so that I can get the profile equation. So this is what the equation is there. So after integrating this equation, so I will get this equation. So tau xz equals to rho g cos of beta into x plus c1. To get this one constant, this constant c1, I need at least one boundary condition. So at least one boundary condition is needed. So and then we have observed this problem. So this is our problem actually. So this is whole film. So total film. So length, okay, z. Length is z direction. So where length is total L, width is y direction W, and thickness is delta. This is delta. This is the total thickness of the film. So one boundary condition is needed, that is that to be flux. Flux boundary condition at some value of x should be given. Then only I can solve this equation and get the profile equation. While observing this equation, this is the topmost layer. Okay, this is the topmost layer. So where there is a liquid air interface. Okay, this is the topmost layer where there is a liquid air interface where I can define a flux, and that is equals to this condition. So boundary condition C, okay, this C, gas liquid interface, okay, that gas liquid interface plane, interfacial plane. So there flux will be a zero flux condition at gas liquid interface, which is nothing but at x equals to 0 for all value of z and w on this top layer, or here. Okay, um, if you go to our figure, so this top layer, okay, this top layer where I have gas liquid interface. Similarly here, this on top layer, this is the top layer where a flux will be equals to 0, and this is happening because so there will be continuity of flux. Okay, so fluid interface, if you consider, okay, fluid interface, there will be continuity of flux, and viscosity of the gases are very small as compared to viscosity of liquid. That is why the liquid will not be able to exert any of the shear stress. Okay, because viscosity of the gases are very small as compared to viscosity of liquid. Hence, gases will not be able to exert any of the shear stress or negligible shear stress on a liquid. That is why their flux condition will be 0. And mathematically, if I write here at x equals to 0, tau xz equals to 0. In fact, tau xz equals to 0, tau zz equals to 0, tau xy equals to 0. You take any tau, tau xz, yz, whatever tau you think, but at gas liquid interface, all taus are equals to 0. So here we are discussing tau xz. So tau xz equals to 0 at x equals to 0. This should be, because I have differential equation with respect to x, so I need the boundary condition with respect to x only for solving that equation. That you need to remember. If I have differential equation x and y, then I will be needing the boundary condition with respect to x and y. So same thing will be there when you will go for multivariable differential equation, not multivariable, multi-dimensional differential equation. This is 1D differential equation, and variation is there only in x direction. So I need a boundary condition only in x direction. So mathematically, how to write this? This is what I can write at x equals to 0. So at x equals to 0, tau xz equals to 0. Now substituting this information in this equation, I can get the value of C1. If I substitute x equals to 0, this term will be equals to 0 and tau xz equals to 0. So it is giving me C1 equals to 0. So overall equation reduces to C1 equals to 0 and substituting C1 in this equation, so I will get a flux profile. This is called as a flux profile. Flux profile means a model equation which will define the variation of flux at different location in given geometry. Okay, given system. So now here you can see at different values of x. Anyway, flux is not varying in z direction, or that we are discussing x flux. Okay, z momentum, how it is transported in x direction. Okay, momentum flux in x direction and variation with respect to x. This is what we got actually. So at different value of x, I can get a different value of flux. Okay, and if you plot this, okay, pictorial representation, this will be a momentum flux distribution. This figure, okay, this figure is a flux distribution. Okay, flux distribution, how it is shown? So it is shown just the magnitude. So this will be the magnitude of the flux at the plate. This is my plate. Okay, this is my plate. This is liquid film of delta. This is the liquid film thickness of delta from here to here. And here is my solid plate and fluid is flowing over here. It is flowing over here. And this is the flux profile. So at this plate, what will be the magnitude of the flux? It will be rho g cos of beta into delta. X equals to delta. Similarly, at different value of x, I can get a flux, momentum flux, and at x equals to 0, momentum flux equals to 0. So this is the momentum flux profile. This is momentum flux profile. So we have discussed till this point and we'll continue our discussion. Anybody has any confusion over here? Okay. Now here what we can do is, now tau xz is related to velocity by using Newton's law of viscosity. So how tau xz is related to velocity? So tau xz is related to velocity by using Newton's law of viscosity. So now to get the velocity profile, I need to introduce the Newton's law of viscosity. And after simplifying everything, generalize Newton's law of viscosity. So Newton's law of viscosity, tau xz equals to minus mu dvz by dx. Okay, because liquid is there, second term will not be there, and dx, vx equals to 0, that term will be also 0. So overall, so I will get tau xz will be equals to minus mu dvz by dx. Okay, and this negative sign indicates velocity is increasing with decreasing value of x. Velocity is decreasing with increasing value of x. You can see here. Here velocity is maximum. Here velocity will be maximum. Here velocity is 0, and this is my x direction. This is my x direction. As I am moving in x direction, so velocity is decreasing, x is increasing. So dvx by dz, dvx by dvz by dx, dvz by dx will be negative, hence minus sign will be there, minus mu dvx vz by dx. Now substituting this, and this will be the differential equation with respect to this thing. So now integrating this equation. So integrating this equation, what I will get? Again, this is very simple integration. So rearranging the equation and integrating this equation. So with respect to x, integrating with respect to x, so what I will get? So this is x square by 2. So x square by 2. Vz is rho g cos of beta by 2 mu x square plus c2. Now for solving this equation, to get the final form of this equation, this constant can be estimated by using one boundary condition with respect to velocity. So whether I have any one velocity boundary condition here. So I now here, so previously to first I will get a differential equation with respect to shear stress. There I need a shear stress boundary condition. Now this is the first order differential equation with respect to velocity. After solving that equation, substituting the constant value, I will get a first order differential equation with respect to velocity. And here I need a velocity boundary condition. Okay, velocity boundary condition. So any velocity boundary condition is available. Roll number 20, Aviral.
Yes, sir.
Yeah.
Hello.
Any velocity boundary condition is available to solve this problem?
Yes, sir. Sir, we can say that, sir, at the bottom, sir, velocity will be 0.
Oh, why?
Sir, sir, no slip boundary condition, sir.
No slip boundary condition. How to define that mathematically?
Sir, mathematically.
At x equals to what value, velocity equals to 0?
Sir, at x equals to, sir, delta.
Very good. So you can see this is my origin. So if I move by distance delta, so I will be reaching this bottom surface of the film. This is nothing but this surface. At this surface, here I will have liquid solid interface. Okay, liquid solid interface. And at liquid solid interface, according to no slip boundary condition, the velocity of the liquid will be equals to velocity of solid, and solid is at steady condition. So this plate is not moving, plate is steady. So certainly first layer of the fluid here will be having a velocity 0. That boundary condition I can put. Okay, I can put that boundary condition. So that can be categorized into solid fluid interface plane, no slip condition. So A type of boundary condition. So A type of boundary condition, using A type of boundary condition. So this can be defined mathematically. So at x equals to delta, you can see this is at x equals to 0. So if I move delta, I will be reaching this interface. This is liquid solid interface. At this surface, velocity equals to velocity of solid, that is equals to 0. So at x equals to delta, velocity equals to 0. Now substitute this boundary condition here and get the value of constant C2 and rearrange this equation to get the velocity profile. Okay, substitute this x equals to delta, get the value of C2 and substitute this C2 in this equation, whatever C2 value you will get, rearrange the equation, that will give you velocity profile equation. Problem number 21, Sahil.
Sir.
What is the value of C2?
C2, sir, rho g cos b minus rho g cos beta by 2 mu into delta square, sir.
Minus will come, C2 equals to?
No, sir. Minus, no, sir. Rho g cos beta by 2 mu into delta square, sir.
Okay, and what will be the velocity profile?
Velocity profile, substituting Vz is equals to substituting into this rho g.
And rearrange the equation.
Yes, sir.
So
Yes, sir.
this C2 is rho g cos beta divided by 2 mu delta square. Okay, delta square will come here. Substitute this, get the value of C2 and substitute this value C2 in this equation, get the value of velocity profile. So this is the velocity profile equation. Rho g delta square cos beta divided by 2 mu 1 minus x by delta square. Okay. Okay, this is the rearrangement. This is the velocity profile. Everybody is getting this velocity profile. Roll number 24.
Sir.
Have you got this velocity profile?
Yes, sir.
Okay. So, can anybody just give some input regarding the rearrangement of this velocity profile and flux profile? So there can be many ways to rearrange the equation. Why these equations are rearranged in this format? Can anybody give any input? Why these equations are rearranged in this format?
Hello, sir.
Yeah, tell me.
Sir, velocity is proportional to x square.
Okay.
So the proportional relation is shown in this equation, and tau x it is proportional to x linearly.
Yeah, but why this is arranged only in this format? So you can see whole bracket is there here. Here this is
We
the
can
constant.
directly predict the nature of the graph which the velocity profile will be
Yeah,
obtaining. Like
that is one thing you can expect the graphical nature of velocity profile just observing the equation, and most importantly you can get back your boundary condition very easily. So whenever you are rearranging the equation, the rearrangement should be such a way that you should get back your boundary condition very easily. What are my boundary condition? At x equals to 0, flux is 0. So you put x equals to 0, flux equals to 0. So now almost this is kind of cross check whether your flux profile is correct or not. You put x equals to 0, you will get flux equals to constant. So I am getting back my boundary condition very easily. Okay, and here also at x equals to delta, my velocity is 0. You can see if I put delta here, so 1 minus 1 equals to 0 and velocity equals to 0. So need not to do much calculation to get back my boundary condition. My both the boundary conditions are satisfying, and I can get back my both the boundary condition using velocity profile and flux profile easily. So all the time whenever you are rearranging the equation, so you should target rearrangement, because there in mathematics there can be more than one number of ways to solve the problem. Okay, so rearrangement, okay, you can go as per your own rearrangement. It can be anything. You can take x constant, you can take delta constant, you can take mu constant, you can substitute delta. You can see here also some delta is there, here also some delta is there. Why delta is taken constant and it is rearranged? So it is very easy. Put x equals to delta here, put x equals to delta here. So 1 square is 1, 1 minus 1 is 0. So this bracket is 0 at x equals to delta and vz equals to 0. So easily you can get back your boundary condition. And if you are getting back your boundary condition using a profile equation, so you can make sure that certainly there is a close possibility that whatever profile equation you got is correct. Okay, you can check, you can say this is the cross check. Okay, cross check of this your velocity profile and flux profile equation. That is one important thing you should remember. Now, how many boundary conditions are needed to solve this problem to get the velocity profile? How many boundary conditions are needed to solve to get the final equation for velocity profile? Yeah, anybody? Roll number 14, Anmol.
Yes, sir.
How many boundary conditions are used to get the final velocity profile equation?
Sir, we use the no flux condition to calculate tau xz. So we use the no flux condition and no slip boundary condition at the solid liquid interface.
Okay, so how many?
Sir,
How
two.
many boundary conditions are used to get the final velocity profile?
Sir, two conditions.
Yeah. So to get the final velocity profile equation, I need a two boundary condition. This is the situation when I have only one velocity Vz and it is the function of x only. I need a two boundary condition. The two boundary conditions, one is a flux boundary condition, another is a velocity boundary condition. Same problem can be solved if I have other two types of boundary conditions. Say velocity is given at two locations. Okay, I need a two boundary condition to get the velocity profile. And that can be either one flux condition and one velocity condition. Two conditions are there. Or this problem can be solved also if I have two velocity boundary condition. If say velocity is given at the top surface and velocity is given at the bottom surface, that time also this problem can be solved. Okay, but here I have one flux boundary condition and one velocity boundary condition, and I am able to solve the problem. Okay, but if I have two flux boundary condition, this problem cannot be solved. Okay, so I need a two boundary condition. This two boundary condition should be either both should be of velocity, then I can get a velocity profile, or if I have one flux condition and one velocity condition, I can solve and get the velocity profile equation. So I need a two boundary condition, at least two boundary condition. This is the situation when I have only one velocity Vz and this is the function of x only. If I have Vz which is a function of x and y, how many boundary conditions are needed? If Vz is a function of x and y, how many boundary conditions are needed? Roll number 13, Shiva.
Yes.
How many boundary conditions are needed? Say for example, I have considered velocity Vz non-zero only and it is a function of x and y.
Sir, four conditions.
Four boundary conditions are needed. If say I have Vz and which is the function of x, y and z, how many boundary conditions are needed?
Sir, six boundary conditions.
Six boundary condition. If I have Vx, velocity in x direction, velocity in y direction and velocity in z direction, and all three velocity varying in all three direction, how many boundary conditions are needed? How many boundary conditions are needed? If say I am considering velocity is there in x direction, Vx is also non-zero, Vy is also non-zero, Vz is also non-zero, and Vx is changing in xyz direction, Vy is changing in xyz direction, Vz is changing in xyz direction. How many boundary conditions are needed?
Yes, sir. 18.
18 boundary conditions. So you can see there will be a three simultaneous differential equation. Second order simultaneous differential equation, three dimensional xyz. Three dimensional second order simultaneous differential equation for three momentum, x momentum, y momentum and z momentum. The analytical solution of this is not available till date. Then I am considering all three velocity and it is changing in all three directions. There is no analytical solution available. In fact, when you go from this one dimensional, okay, one velocity varying in one direction to one velocity varying in two direction, that time also it is difficult to get the analytical solution. Okay, that is why so many assumptions are added such that you will get only one velocity and it is changing in one direction. That time only there is a possibility that so you will get a easier model equation. Okay, so all the problems are defined in such a way that in most of the problem you will get a one velocity changing in one direction. Now, what is your expectation? How will be the velocity profile? Roll number 29, Vedant.
Sir, I guess it should be a parabolic equation because we have a x square term here,
Okay.
and it will be like if we consider the origin, it will be slightly shifted downwards, I guess.
Okay. And where it will be maximum velocity? Where you will get maximum velocity?
So for maximum velocity, we can just differentiate this equation and set it to 0.
No.
Or just
Where you will get maximum velocity? From equation itself, you can see.
Acha, in the center, sir. In the center.
Where center? Center of the field
Center
will
of
get maximum velocity.
At no, sir. Sorry, sir. It will be at the interface of gas and liquid.
Yeah. At x
Yes, sir.
equals to 0, you will get a maximum velocity. So
Yes, sir.
this is what the velocity distribution is there, velocity profile. This is parabolic velocity profile. Okay, parabolic velocity profile, maximum at the gas liquid interface and 0. This is no slip boundary condition. This is one boundary conditions we have used, and this is one boundary conditions we have used. Tau xz equals to 0 at gas liquid interface, and here you will have 0 flux condition, and maximum flux will be at the solid liquid interface. Okay, so this is a momentum flux distribution, and this is the velocity distribution for flow or flat plate, and this is subjected to limitation. What is the limitation? First of all, I have 1D flow. Okay, first of all, I have 1D flow. Secondly, delta is very small. Delta is very small, not very small, not very large. Delta is smaller, so that acceleration is negligible. Negligible acceleration, delta is small enough to neglect the acceleration. So velocity is not 0. If say you can see delta is very small, then certainly this velocity will be 0. Okay, so if say delta is very small, you can see velocity will not, the molecule will not move. Just consider one layer here. So delta is not that much small. But delta is not very large. So what will happen? It is increasing maximum. Now here, after some time, okay, after some time, what will happen? This velocity will be constant here. Okay, velocity is constant. Okay, if delta is that much large, okay, delta is large, so what will happen? This viscous forces will be negligible as compared to viscous forces here in bulk of the fluid, because here itself liquid is ending. Say delta is say very large, so in bulk of the fluid, viscous forces are negligible as compared to gravitational force, and then it will start accelerating. Flow will start accelerating. Velocity will increase in z direction. That we are neglecting. So how to interpret that mathematically? How it is explained in mathematically? So Reynolds number is defined for this case. Okay, this is the definition of Reynolds number, where average velocity is a characteristic velocity and 4 into delta is a characteristic dimensions. Okay, characteristic length. You can say characteristic length d v rho by mu. So 4 into delta is a characteristic dimensions. Average velocity is a characteristic velocity, and this is the definition of Reynolds number for this case. Okay, Reynolds number equals to 4 into delta into average velocity into density divided by mu. If say Reynolds number is less than 20, then can consider that flow to be a laminar, negligible rippling. Rippling means wavy nature of the flow. Okay, if say Reynolds number according to this definition, if Reynolds number is between 20 and 500, so then predominant rippling will be there. Rippling means flow will be kind of wavy nature. So there will be a x velocity also, y velocity also, z velocity also. It will travel over a plate in the form of ripples, actually wavy form. Every molecule will form, and that is also laminar flow only. Flow will be in layers, but rippling will be there. And if the Reynolds number is greater than 500, then it will be turbulent flow. So all molecules are moving randomly. all molecules are moving randomly, and whole of this analogy is applicable only when Reynolds number is less than 20. Laminar flow with negligible rippling. That at that time itself we can consider only one velocity Vz, Vx equals to 0, Vy equals to 0 when Reynolds number is less than 20 according to this definition. Why this definition is used? So whoever has given this modeling approach first time, he has defined 4 into delta as a characteristic length and average velocity. This is average velocity, not maximum velocity. This is average velocity in x direction. So you can see, so in previous case, in previously we have discussed, so characteristic length was used from the starting point, okay, from the starting point of, if say this is my starting point, so this length is used as a characteristic length. But here, this researcher is using 4 into delta as a characteristic length. Okay, altogether that meaning is different Reynolds number. This meaning is different Reynolds number. Okay, so hence that range of Reynolds number. Okay, it all depends upon definition of Reynolds number. Definition of Reynolds number. Here, 4 into delta is used as a characteristic length. Average velocity. Okay, there bulk velocity was used as a characteristic velocity. Here, average velocity over delta is used as a characteristic velocity. 4 delta into characteristic velocity into density divided by viscosity. This is defined as a, and this thing is applicable, okay, this thing is applicable only for Reynolds number less than 20. If Reynolds number is greater than 20, this whole modeling approach is not applicable. Okay, you cannot use this model equation to get the velocity profile. Once you have velocity profile, you can get flux profile, you can get maximum velocity, you can get minimum velocity, you can get maximum flux, you can get minimum flux. Velocity profile is very, very important. Okay. So this is true only for laminar flow with negligible rippling. Okay. So what will be the maximum velocity? How to get maximum velocity? Just a couple of minutes before I have discussed this. Well, number 47, Gurupreet.
Yes, sir.
So how to get maximum velocity?
Sir, we will put x equal to 0.
X equals to 0. So what will be the maximum velocity?
Sir, it will be rho g delta square cos beta by 2 mu.
Okay. So at x equals to 0, maximum velocity will be rho g delta square cos beta by 2 mu. Okay. So given the value of, this is the property of system. So given the value of beta, angle of plate, what is the thickness of fluid? Okay, thickness of fluid. These are all constant. So you can get a maximum possible velocity of the film, which is at the top surface. How to get the average velocity? Okay. How to get average velocity? Roll number 61, Rutvik.
Sir,
How to get the average velocity?
sir, we can get the average velocity over the area. This
Yeah.
velocity into the area.
Yeah.
But divided by
Velocity into
the
area divided by area. Anyway,
Yes,
this velocity is not function of y.
yes, sir.
And you can, in fact, you can get 0 to delta Vz by delta x divided by delta x.
Yes.
It will give you same. Now substitute the velocity profile in this equation. Okay, substitute the velocity profile in this equation. This is y varies from 0 to w, x varies from 0 to delta. This is the cross-sectional area. Vz multiplied by area divided by area. That will give you average velocity. So Rutvik, give me the value of average velocity.
Calculating.
Anybody got velocity profile, average velocity?
Hello, sir.
Yeah, Prithvi?
Sir, it came out to be rho g delta square cos
Huh?
beta divided by 3 mu.
3 mu. Okay, this is one and same thing, 1 upon delta. So rho g delta square cos beta divided by 3 mu. So what is the relation between average velocity and maximum velocity? 2 by 3 of maximum velocity. Okay, this is maximum velocity. So this is average velocity. So average velocity is 2 by 3 of maximum velocity. Okay. So once you have this velocity profile equation, you can get all most of the design related parameter needed in momentum transfer. This velocity profile is the most important thing in momentum transfer. Okay. So now mass flow rate. How to get mass flow rate? Here roll number 80. Shravani,
So,
mass flow rate.
sir, mass flow rate. Sir, we have to integrate this this equation.
So you will still integrate that equation. So how it is mentioned in that equation? What is the logic used in that equation, which is shown on slide? That is what I am asking. How to get mass flow rate?
Sir, we have to integrate it and divide by.
So how you are getting mass flow rate using the equation? That I can see. We need to integrate. We need to integrate. We need to integrate. Again, I will add one time. We need to integrate. What exactly is done to get this mass flow rate? What is the meaning of integration that there? What is shown on a slide? What exactly we are doing to get the mass flow rate?
Divide by volume.
Divide by volume.
No, sir.
So how to get mass flow rate? General. How to get mass flow rate?
Kg per sir, like dimensionally
kg
kg per
kg per second. So how
per
to get that?
second.
Now I have velocity profile equation.
Um, Sir,
So number
velocity profile
96.
into.
Saurav. Roll number 96. Saurav.
Yes, sir.
Yeah. Can you tell me how to get mass flow rate?
Yes, sir. The average of velocity into density, sir.
Huh?
The rho into velocity into area. Rho is density.
Array, you that equation I can read from slide. I'm just asking what is done there actually. Rho into velocity into dx into dy integration over 0 to delta 0 to w, that is done. So whether this is correct or wrong, first of all.
Excuse me, sir.
Yeah.
So, sir, there is like density is mass upon volume,
Okay.
and
Very good.
the velocity is in z direction, and
Uh-huh.
dx dy are becoming area. Then area into that z direction is becoming
Uh-huh.
volume. and that
Okay.
velocity already have that unit of length upon time scale. So
Okay.
that volume upon time scale, then volume and the denominator of density volume will be cut down and cancelled, sorry, and then it will ultimately become mass upon time scale.
Okay. So now, Aditya, can you just tell me physically what exactly we are doing in this integration?
So here actually we are taking that small element what we have considered earlier,
Okay.
and we are integrating over whole thickness of delta
Okay.
and the width
So what
w.
exactly here we are doing is we are averaging the velocity and multiplying it by area. Okay. This average velocity is multiplied by area multiplied by density. So what this integration is giving me is average velocity multiplied by area multiplied by density. It is a mass flow rate. You can go here. Here actually this area. So if I multiply this area here, okay, so this will get cancelled out. So what is average velocity? Average velocity is summation of velocity over this differential divided by the integration of differential. This integration of differential is area multiplied by this area. So I will get this equation. This equation only numerator, what is only numerator? It is the average velocity multiplied by area and multiplied by density. Multiplied by density will give you mass flow rate. So now this average velocity multiplied by area. What is the cross-sectional area? What is the cross-sectional area for flow, Aditya? Aditya, roll number 4.
So xy plane.
XY plane. So what is the cross-sectional area? It will be W into delta.
Yes, sir. W into delta.
So this average velocity multiplied by W into delta multiplied by rho will give me mass flow rate. Okay. This is density. Okay, this is density multiplied by cross-sectional area multiplied by average velocity. This is what done here actually. Will give you mass flow rate, and that is equals to, this is average velocity, substituting this. So rho square G W delta cube cos beta divided by 3 mu will give me a mass flow rate. Mass flow rate of the liquid film flowing over a flat plate. Okay. Everybody got this equation? Okay. What is the drag force exerted by flowing fluid on a flat plate? Roll number 90, Priyank.
Yes, sir.
What is the drag force exerted by flowing fluid on a
Sir,
plate?
it is the area, characteristics area into kch into friction factor.
So, for this case, I am asking.
For this
There is
case,
friction
it will
factor
be
here.
flux into differential area.
Flux into differential area.
And we will integrate over 0 to W and 0 to L.
0 to dow and 0 to L. Okay. 0 to
W.
W and 0 to L.
Yes, sir.
Okay. So what you will get? So that will be a area. This is mass flow rate. So now using mass flow rate, you can measure this mass flow rate. You can collect the liquid coming down the plate and calculate mass flow rate, and you can measure the value of delta. Similarly, you can measure the value of average velocity using volumetric flow rate, and this will be used to get the value of thickness. So reverse calculation also, how to get the value of thickness. this using mass flow rate and using average velocity. Now this is the drag force. Okay, drag force exerted on solid fluid. The force per unit area. So this will be a area will be a L into W. This is the plate area and tau xz integrated over dy and dz. Anyway, this tau xz is not changing in y and z direction. So you can estimate the a shear stress at x equals to delta. At x equals to delta. This is evaluated at x equals to delta at the surface multiplied by surface area. So that will be equals to this. You can have flux profile also. Using flux profile, you can get the shear stress at x equals to delta multiplied by W into L will give you drag force. Okay, or you can differentiate the velocity profile multiplied by minus mu and that estimate at x equals to delta and multiplied by L into W, that will give you drag force. So what will be the drag force exerted by flowing fluid on a plate? Priyank?
Sir, it will be LW into mu into rho g delta cos beta by mu.
Rho g cos beta delta divided by mu. So this is the velocity profile. Either you can integrate or you can use a flux profile also. This flux profile is also we have. You can estimate that value at x equals to delta or differentiate this equation with respect to x. Substitute x equals to delta. Get this value. Multiplied by mu multiplied by L and W. So you will get this. So this divided by dx. So that you can do. Okay. It will give you rho g delta LW cos beta. Okay, this is the drag force exerted by flowing fluid on a plate. Okay, now you can see these are all design important parameter. What are design important parameter? Most importantly, mass flow rate is a design important parameter. So you can get a mass flow rate. Volumetric flow rate is a design important parameter that you can get using this velocity profile equation. Average velocity is one of the important parameter. Flux profile is one of the important parameter. Drag force by flowing fluid on a plate, that is one important parameter. Everything you can get using this velocity profile equation. This is clear? Anybody has any doubt? Okay, solve this numerical. Take down all the data from this numerical and solve this numerical. Pritesh, roll number 88, Pritesh.
Yes, sir.
Do you have class at 3 o'clock?
We have lab, sir.
Okay. So solve this problem and then we'll continue in tomorrow's class.
Okay.
Kinematic viscosity is given. This is viscosity divided by density and density is given. So you can calculate the viscosity. So falling film of thickness is given 2.5 mm and 1 meter wide. Width is given. On vertical wall. Vertical wall is, so what is the beta equals to vertical wall? What will be beta equals to for vertical wall?
0 degree, sir.
0
Zero,
degree.
sir.
0. So what should be the mass flow rate of the film? Check the Reynolds number or whether it is applicable or not. So first you get the mass flow rate and then you can use this data to get the value of Reynolds number. So you can obtain the Reynolds number by using mass flow rate also. Very easy problem actually. So this is the mass flow rate. So density is given, gravitational force is given, width is given, yeah, delta is given, cos beta is given, mu is given, everything is given. Okay, so this is 0.2 kg per second. Anybody else getting any other answer? Now to get the Reynolds number, okay, this Reynolds number is 4 into delta average velocity density divided by mu, and this average velocity into cross sectional area into density is a mass flow rate, and I have already mass flow rate. So I can substitute that here actually. So you can see this mass flow rate is density multiplied by cross sectional area into this. So instead of this average velocity, I can use this mass flow rate divided by density divided by mass flow rate divided by density into W into delta here, and you can get the all other things are known. Delta is known, density is known, viscosity is known. This mass flow rate is just now calculated, density is known, width is known, and this is delta is known. So this is what I am telling. So Reynolds number will be equals to 4 into delta into mass flow rate divided by density with delta. So this density will get cancelled out. This delta will get cancelled out. Okay, so what we will get, 4 into mass flow rate divided by W into nu. Okay, this is viscosity divided by density. Viscosity divided by density into rho or mu. This is mu. Actually. So you substitute this and you get a Reynolds number value. What is the Reynolds number value? Roll number 111. Vipasvi 111.
Yes, sir.
What is mass flow rate? What is mass flow rate you got?
Sir, it is 0.204 kg per second.
Have you calculated that?
Yes, sir.
Can you show me your notes? Just switch on the camera and show me.
Yes, sir.
I cannot see actually. Just hold on. Okay. Okay, fine. And what is the Reynolds number? What is Reynolds number? Yeah?
Sir, it is coming 5.
5. Okay, so this whole modeling approach can be used actually. So this is true for Reynolds number less than 20. Okay, now just concentrate everything. This is homework for you actually. So this is the 3D view of the film. How many origins are possible? How many origins are possible? The roll number 6. Roll number 6 is not there. Roll number 4, Aditya.
Yes, sir.
How many origins are possible for solving this problem? Possible origin.
So again, 2, sir.
Why 2 only?
So because we have to always simplify our problems.
Okay. So, but actually there are 8 possible origin. These all corners, no? So you can take everywhere this problem will be as simple, because your axis will be aligned with your boundary and your flow will be along with your axis. If you take origin here, 4, 4 and this 4 bottom, there are 8 possible origins. So now you tell me, if I change the location of the origin, whether my model equation will change.
So maybe the signs, but not all together.
Why not? Look, there are 8 possible origins. This is 1, 2, 3, 4 and 4 are bottom. Okay, these are the 8 possible origin. Now say I am moving in y direction, I am moving in z direction, I am moving in y direction. Okay, if I am moving in y and z direction, my model equation will not change, because my Vz is a function of x only. But if I am moving in x direction, change the origin, okay, then certainly I will get a different model equation, because my velocity is a function of x. I will get a different model equation. So for top 4 origin, I will get one model equation which is already solved, and for bottom 4 equation, 4 origin, I will get a different model equation. So now your homework is solve the same problem using the origin here. Okay, using origin here. So just briefly, I will explain what you will get here actually. So this is what changes will be there. This was our previously, x varies from x to delta x. X was top. I am going from top to bottom. Now it will change. It will change. This was previous. Now x will be bottom and x plus delta x will be top. I am going from top to bottom. Okay. So and this will be the equation I will get. Tau xz will be equals to minus rho g cos of beta, and this Newton's law of viscosity will be positive. You should not be taking negative here, because velocity is increasing with increasing value of x. So this is positive. So negative sign is not needed here. And this is the boundary condition. At x equals to 0, Vz equals to 0. And at x equals to delta, tau xz equals to 0. Exactly reverse the boundary condition. This is the flux profile I will get, and this is the velocity profile I will get. So you can see now, if I put x equals to 0 here, okay, x equals to 0 here, I will get velocity equals to 0. And if I put x equals to delta here, I will get a flux profile. You solve and get this equation. Homework. This will be homework for you. Okay, what is homework for you? So as I told, if I change at this 4 point, you will not get any change in my model equation. But if I change in x direction, there will be variation. Solve same problem using the origin at the bottom. So you are expected to get this this flux profile equation and this velocity profile equation. Okay, try solve and try it on your own. And if you are getting any problem, so we'll be discussing that problem. What if you are getting a problem? If you are not getting a problem, we will move on to next problem. Okay, next case for study actually. Okay, then see you in tomorrow's class.
Hello, sir.
Yeah, tell me.
Sir, they are asking if you can share those previous year papers which you were talking about that you will share.
Yeah, I'll share with you.
Okay, sir.